of q alpha minus p times q. Okay, so let me explain what this quantity captures. So first of all, we saw many times in the conference, let's recall that the number alpha is badly approximable, or it's a bounded time number, if and only if there exists a constant such that alpha minus pq is greater than constant over q squared for every p and q. So if you have a number of bounded type, okay, you can multiply this by q squared. Or if you want to, this is q alpha minus p greater than c. So this quantity q alpha minus p is bounded below uniformly in qp, and this lim sup will be finite.
Do you want p to be the nearest integers of q alpha?
No, I can, well, this would be, you can write it like this. It's going to be achieved by the nearest integer. No?
Wow.
Do you prefer if I write this? Sorry, do you want to prefer if I write integer part or something like this? Well, you know. Okay, you want to, I can write like this if you want.
Yeah, that feels better.
Okay, and okay, so in particular, actually, this value L of alpha will be finite if and only if alpha is bounded, is badly approximable. So, sorry. Sorry? I made a mistake. I'm sorry. It's lim sup of 1 over. My apologies. My apologies. Yeah, this is defined like this. It's lim sup of 1 over this quantity. Apologies. I already confused everybody. Yes. So this quantity, yeah, you want to, yeah. Yeah. Sorry, I apologize. It's 1 over, yes. Okay, so it will be finite. Okay, so this quantity will be bounded below when it's badly approximable, so this lim sup will be finite, okay? For almost every alpha, the value will be simply plus infinity. So this value really, this Lagrange spectrum is constantly equal to plus infinity unless alpha is bounded type. And what we are looking at essentially is sometimes the set of constants which are optimal here asymptotically. So in which case, let's say 1 over L of alpha is going to be the sup of the constants such that alpha minus pq is greater than constant over q squared for all pq large. So eventually, okay? So we are looking at the set of constants which appear, optimal constants which appear attached to a bounded type irrational number. And okay, there is another interpretation of this that I don't want to spend time on, but if you prefer geometry instead than number theory, you can use Dani's correspondence between bounded geodesics on the modular surface and badly approximable numbers. So I'm not going to write anything, but I'll just say it in words. Maybe I can actually say a remark. So L is also, let me call it a penetration spectrum. The penetration spectrum of bounded geodesics on the modular surface of bounded geodesics on, let's say, SL2R mod SL2Z. So you're going, if you consider geodesics which stay in a bounded region of the modular surface of SL2R modulo SL2Z, you can and choose the suitable proper function to measure the distance in the cusp. What you have to consider is, because you have this lim sup, you want to look at the omega limit set of a bounded geodesic, so the set of forward accumulation points, and then measure the size of the smallest compact set that contains the omega limit set of a bounded geodesic. And the set of these diameters of compact sets is what you are capturing in the Lagrange spectrum. And another remark is that if instead of lim sup you consider the sup, then you get a very related object, which is the Markov spectrum that maybe more people in this room know about because of the relation with values of quadratic forms. Okay, and I want to just review a few of the main results that are known about the classical Lagrange spectrum. In particular, so first of all, L is a closed set. And it's also obtained, you can just restrict yourself looking at alpha, which are quadratic irrationals, and take the closure. So it's the closure of the values achieved. Basically, in this picture, you can just look at closed geodesics on the modular surface. And this is a result due to Cusick. And since I have some dates, let me put them in. So this is quite late, it's 75. But now I want to kind of draw a picture of how the Lagrange spectrum looks like. And so it's a closed set, so there is a minimum, and which is achieved. And the minimum here is the inf of L is the square root of 5, and this is achieved by the golden mean, as you may expect it. And this is a result due to Hurwitz, one of the first results. And this is called also Hurwitz constant, and it's from 1891. And then there are some values which are discrete. So the beginning of the spectrum up to 3 is the first accumulation point. So here there is a discrete part, and this is discrete. And this part actually coincides with the Markov spectrum. So this is indeed proof, the fact that the Markov spectrum here is discrete is due to Markov, and it's one of the oldest results. It's from 1879. And then at the other end, this is what I want to focus on today. At the other end, from a certain point on, you can show that there is a whole semi-line contained in the Lagrange spectrum. So, but what I want to write here is that this is what is called Hall's ray, because it was proven by Hall. So Hall's ray, so there exists an R such that the semi-line R plus infinity is contained in L. Okay? I think Hall actually proved in 1947. He proved actually that you can take 6 as a beginning. From 6 on, you have a full ray. But you can try, of course, to improve the value where the whole ray begins. And the optimal beginning, so this is actually constant L, which is due to, maybe let's call it F. This is due to Freiman. And, okay, I don't know the year here, but it starts at actually 4.2.527, something. Okay, it's a quadratic irrational, but okay, you can write. And in between, what happens in between? Actually, okay, this is a research which you see started in 1800, but results of what's happening in between are more delicate. And there was some recent work, for example, by Moreira, which is in 2000. And essentially, here there is a Cantor-like structure between this discrete part and the whole ray. And I'm not going to write anything, but so Moreira, for example, studied, it looks at level sets, so he takes the value t between these two parts and intersects with the Lagrange spectrum and looks at the Hausdorff dimension of what you have. And you can prove that the Hausdorff dimension is changing continuously and monotonically. And essentially, you would see something like a Cantor staircase if you plot the graph of the Hausdorff dimension. Okay, so this is all for the classical Lagrange spectrum. And there have been plenty of generalizations of the Lagrange and the Markov spectrum, especially thinking of this geometric point of view, thinking of this penetration spectrum when you have a non-compact space and with some negative curvature. And for example, the first thing you can do, you can take another Fuchsian group instead than SL2Z. And for example, there are results by Series and Haas, and then many papers by Bullock studying the Hurwitz constant and the beginning of the spectrum. And yeah?
Is the Freiman result sharp?
Yes, this is sharp. This is the beginning of the whole ray. Yes, that's then there is a gap. The first gap. Mm-hmm. And then you can, there is actually, Mokuran is not here, but Mokuran was one of the first who then looked at Markov and Lagrange spectra for higher dimensional hyperbolic manifolds, and especially for the Bianchi group. He had some motivation from Diophantine approximation in imaginary quadratic fields, and he proved the analog of this result about closure and density of periodic orbits. And then Paulin will be here next week. I missed the two main experts on the Lagrange spectrum. So Paulin also has done lots of works, joint work with Parkkonen and with Herskonsky, proving several generalizations of the Hall ray and closure and density in the context, again, of negatively curved hyperbolic manifolds in higher dimension. Okay? And what I want to talk about today, which all starts from this joint work with Pascal Hubert and Luca Marchese, is what is the Lagrange spectrum in the context of translation surfaces. So again, here another. Some people are experts, some people are not, but I'm not going to really spend any time giving formal definitions. So I want you to think of a translation surface simply as a polygon. For example, take the regular octagon, for this talk is a good example, and just glue in these opposite sides which are parallel by parallel translations. So in this case, so let me call the surface, you can think of it as a polygon with pairs of opposite parallel sides identified by translations. And in this example, you will get a surface of genus 2. And this surface is at almost every point has a Euclidean structure. So points have neighborhoods which look like the flat plane, and they have a flat metric, with the exception of some special points. In this case, the vertices of the octagon are problematic, and they give rise to a point on the surface which has a so-called conical singularity. So it's a point where there is negative curvature, and it looks like a cone. So maybe let me say, I don't want to, again, it doesn't matter for today. Flat metric plus conical singularities. And the only thing that I need about a flat surface, we already heard in the talk by Kadri, if you were here last week, is the notion of saddle connection. So a saddle connection is simply a straight line geodesic. So it's a geodesic on the flat surface, which goes from one of these singularity to another one singularity. In this polygon picture, you can just think of drawing a straight line from one of the vertices. For example, let me go here, for example, yeah, this is something like this. For example, this wedge is, this edge is identified to the opposite, so you might go straight, then you use the identification to continue your straight line until you hit the next singularity, okay? So those are saddle connections on the translation surface. And to each saddle connection, I want to identify a vector in R2. So in this picture, you just want to develop your saddle connection in the plane and look at the difference between the final and the initial point. So this would be the vector in R2, which represents my saddle connection. So this saddle connection displacement vector. Does it make sense to everybody? Yeah. So this is, I would think of this vector associated to the saddle connection, that is also called holonomy vector. I have at least one co-author who doesn't like the name holonomy vector, and so I'll do displacement vector in R2. And R2 I'm going to identify with the complex plane all the time, so I use alternative. Okay, so now I'm going to give you a definition of Lagrange spectrum, a Lagrange value for the vertical direction on a translation surface, which is completely geometrical, but I will convince you later that it gives the same result than the classical definition for the torus. So let me give the, do you see if I write? Can you see if I write on the blue spot? Okay. So I'm going to write L of S. So S is a translation surface, and this is the Lagrange value, and I'm kind of considering, I want to look at the vertical direction. Other directions I'll obtain them by rotating the surface. Okay, Lagrange, this is gonna be the lim sup, and there was a 1 over, that before I forgot. And now I'm going to write the product of real part of V times imaginary part of V. Here I'm thinking of a vector in R2 as a complex vector when I write. And this is the lim sup is taken as V ranges among displacement of saddle connections, and as imaginary part of V grows to infinity. Okay? Okay, so this looks like a pretty different definition, and I want to convince you that it's not. But first, let me make sure that it's clear what I'm doing. So I'm looking at the vertical direction, and then I'm looking at vectors. So maybe let me do something this. So this quantity, the product of real part of it, some imaginary part, sometimes we also like to call it area of the vector. And what does it mean? If I have a vector, V, and I'm taking the product of real and imaginary part, I'm just computing the area of a rectangle which has this vector as a diagonal, okay? And sides are horizontal and vertical sides. Okay, this is area of a rectangle with V as diagonal. So I'm looking at vectors which have larger and larger imaginary part, and if I'm trying to compute this lim sup of 1 over, you want to make this area as small as possible. So as I'm looking to find this lim sup, as I'm looking at vectors with higher and higher imaginary part, you want to look at the ones which have exceptionally small area, so which have very small real part. Those will achieve the lim sup. Does it make sense? Okay, and now I don't know if I have enough space, probably not, okay, let me go up and erase the history of the Lagrange spectrum.
So the definition of L shouldn't have a bar, right?
Sorry?
The script L that you define.
Where?
There shouldn't
script
be
L.
a bar on it.
No, this is the bar when I take quadratic irrationals. Sorry? Then the definition, there is no bar. Bar, you mean closure?
I see.
So
okay.
this is the definition, is all values are in RA,
so
and this is a result by Cusick that you can only compute quadratic irrationals and take the closure. And you get the same set. So that's why there is a bar there. Okay. So I want to convince you that this is really a generalization of the torus definition, at least heuristically. So the torus of the classical Lagrange spectrum. So how do I recover the classical Lagrange spectrum? So if I take as my surface, say the unit, the torus, the standard torus, then okay, I still have the definition, I have both definitions here, which is good. So for the standard torus, I claim the following, that the Lagrange spectrum, you can obtain it as the following. So, maybe let me see. Okay, this is the standard torus. I want to take some angle theta with the vertical. I want to look at the direction in angle theta. And to study it in this definition, I only define Lagrange value for the vertical flow. So I want to compute Lagrange of r theta of S, where this is the torus that I obtained by rotating so that the angle theta is vertical, right? So I want to rotate to make it vertical. And I claim that this value is actually the same than, well, I have the same L. It's the same that the classical Lagrange value for alpha, where alpha is the cotangent of theta or something like this, and I'll convince you of this. So the classical Lagrange spectrum will be just the set of values defined geometrically in this way as I rotate my surface. So this is what I claim. Okay, so let's say that I want to compute the classical Lagrange spectrum. So maybe I need a color. Let's say blue, should go blue. So I take my slope, this is an angle theta here. And then, so first of all, what are saddle connections? Well, saddle connections in the square torus are given exactly by coprime integers. So if I have a vector which is of the form PQ with PQ coprime integers, this projects exactly to a saddle connection on the torus. So now look at your favorite, look at any coprime PQ. So I claim, let me draw a picture. I claim that when I compute the lim sup of 1 over Q integer part of Q alpha, I'm actually looking at 1 over the area of this blue parallelogram. So I claim that 1 over Q alpha, maybe Q alpha is the area of P parallelogram. And you can see this because this parallelogram has height Q. And I don't know, this line is Q alpha comma, this point is Q alpha comma Q because it's on a line with cotangent alpha slope. And this area of this parallelogram is really integer part of Q alpha, or Q alpha minus P. So I'm looking at areas of parallelograms done in this way. This is the classical definition of the Lagrange spectrum geometrically. Does it make sense? And what about my definition? Okay, in the other definition, you should turn your head. So you should look at this slope as your vertical. And then I'm gonna, for each the correction, for each PQ, I'm gonna compute the area of this rectangle, of the green rectangle. So it's not exactly the same quantity, but it's an area which differs from the area of the parallelogram by these two small triangles. And this you can think of as an error term. So asymptotically, as this area grows, you can show that this, the difference is negligible. So when I compute the lim sup using parallelograms or using rectangles, you actually get exactly the same value. Does it make sense? Okay, so hopefully I convince you just that this definition is a generalization of the classical world. And now I will erase the classical world, and we will stay with Lagrange spectrum of translation surfaces. So before I want to, well, maybe at first I want to recall some other thing. I want to record that if you look at SL2R, this actually acts on translation surfaces in a natural way by deforming linearly a translation surface. So I don't know, if I had a polygon, and this is the surface obtained by gluing the polygon P. On the polygon P, I can just act linearly by a matrix, by the linear action in the plane. So I will get some, I don't know, deformed linear. But parallel lines are still parallel in the new picture, so I can still glue parallel opposite lines. And this, by definition, is the surface A acting on S. So acting on S linearly by A means acting linearly in the plane and then redoing the gluing. Okay. And what did I want to say? Yes, I want to say what is a Veech translation surface. I'm not going to be very precise, but it's useful to you. So let's say that a translation surface is a Veech translation surface. So these are special translation surfaces, which have the property that when you act by SL2R and look at the closure, this is what I'm like. So this surface lives in the moduli space of translation surfaces that I don't want to define. So you're changing a translation surface and there is an equivalence relation between translation surfaces. And in this space, I want to take the closure of the orbit. But the main thing that if the special translation surfaces have the smallest possible orbit closures. So the orbit closure has actually the same dimension than SL2R. So this is actually closed already, and it's isomorphic, say, to SL2R modulo a lattice. Gamma is called a Veech group, and is a lattice. And it's going to be non-uniform. There will be cusps. There will be a non-compact. So what I want to say that when you deform your translation surface by acting by SL2R, the space of deformation is a hyperbolic, the unit tangent bundle of a hyperbolic surface. And the prime example you should have in mind is if S is the two-dimensional torus. If S is some torus, some flat torus, then you get the modular surface here. So the Veech group is SL2Z, and the space of flat tori is parametrized by the modular surface, the unit tangent bundle of the modular surface. And the second next example that is good to have in mind is if S is a regular two-angle, for example, let's say is an octagon. If it's a regular octagon, or more in general, any regular polygon with even number of sides. Veech showed that regular polygons, when you glue them and obtain a surface, give you a Veech surface. And in this case, gamma is essentially it's isomorphic to a triangle group. It's a triangle group of the type, I think, 4 infinity, infinity. So, okay, in this case, so here you have the modular surface, and here you will have some surface which has actually 2 cusps. So the space of deformations of the affine deformations of the regular octagon is parametrized by a hyperbolic surface with 2 cusps. Okay? Okay, let's see where I am. Okay, I hope I don't want to say any more about Veech surface. But what I want to say that, so okay, if S is a Veech surface, so I will define the Lagrange spectrum of this Veech surface as the set of values L computed at r theta of S as theta changes in the unit circle. So I'm looking, remember the definition that I gave before was this definition for the fixed vertical direction looking at areas of saddle connections. And the Lagrange spectrum is just a collection of the values that I obtain as I rotate. Okay? So this is what I call the Lagrange spectrum of a Veech translation surface. So now we have defined all the terms in the title. I think we have all whole array, Lagrange spectrum, Veech surface. But I could state the main result, but first I want to say something about more in general. More in general, you can consider, let's say, I, I'm calling I, and any SL2R closed invariant locus. By that I mean any subset that we write, closed invariant locus of translation surfaces. So look, any subset of the space of translation surfaces, which is invariant when you act by SL2R and which is closed. So this example, SL2R mod gamma, was one example of an invariant locus. It's the smallest possible. The largest possible could be a connecting component of a stratum of translation surfaces. And in general, now we have this great theory due to Eskin and Mirzakhani that tells us how this, and Mohammadi, yes, sorry. Yeah, sorry. No, that tells us how this, that these closed invariant locus in general are nice in the sense they are affine in the suitable coordinates. So they're, okay, and then if I have a closed invariant locus, you could define the Lagrange spectrum of the locus as the union of all values achieved as your surface varies in the locus. Okay? And okay, so this is the object that we consider in the joint paper with Pascal Hubert and Luca Marchese. So in this paper, first of all, we give this definition, but another thing which I didn't say, that this is only one of the possible definitions. One thing that we show in this paper, okay, there are equivalent definitions, and you can especially, there is a Diophantine approximation flavor definition, where you can define the same quantity using interval exchange transformations, and using badly approximable interval exchange transformations and defining constants, which are similar to the classical definition. Or you could also define the same object by looking at bounded Teichmuller geodesics in the moduli space of translation surfaces and looking at the penetration spectrum with respect to a suitable function, which is the systole, or the shortest length of the length of the shortest saddle connection on the surface. Okay, there are more geometric and more Diophantine definitions. Okay. So, okay, in this, so apart from giving this definition, so for example, one thing that we show that for any I as above, so for any closed SL2R invariant locus, you can show that, let's see if I have space for 3 things. So L of I is closed. So second thing, L of I is actually the closure of, this I'm gonna be mysterious, but it doesn't matter. This is the closure of surfaces which have a pseudo-nosov, have a S such that the vertical direction is fixed by a pseudo-nosov, and I'm not going to say what this is, but this is the suitable generalization of quadratic irrational, and this is something that corresponds to closed Teichmuller geodesics. So this is analogous. These two are analogous to the results by Kuzik on the classical spectrum that tells you that the spectrum is closed. There, it's the closure of quadratic irrationals. And the third thing that we prove in the same paper is that if I contains space is running short, a square-tiled surface. Okay, let's say 1 second this. Then L of I has a whole ray. Okay, so we prove something about the existence of whole ray, but we need this assumption that the locus contains a square-tiled surface. So maybe I'll draw a picture here. A square-tiled surface, it's a surface which can be paved by, say, squares, regular squares. And these surfaces are dense in general in space utilization surfaces, and they are just branched covers of the square torus, say. Okay? So if we have one special surface like this, then we prove that there is a whole ray. And okay, of course, it's kind of annoying that you have this assumption because, okay, what if there is a locus which does not contain square surfaces? And there are loci which don't contain square surfaces. There are more complicated ones. But especially if you just take, for example, the regular octagon and look at as locus the SL2R orbit of this regular octagon, it will not contain square-tiled surfaces. So, for example, this does not apply to Veech surfaces, to the Lagrange spectra of Veech surfaces which are not square-tiled. Okay? So the main theorem that now I would want to focus on is, as I said, in joint work with Mauro Artigiani and Luca Marchese. And so the theorem, this is Artigiani, Marchese, and myself. And this is the title. So for any S Veech surface, there exists a whole ray. So there exists some constant, L of S, such that L of S, comma plus infinity is all contained in the Lagrange spectrum of the surface S. Does it make sense to everybody? Yeah. Okay. And in particular, if you have a locus and that contains a Veech surface, you also have a whole ray. Okay, so what I want to do in the rest of the talk is actually to try to give you an idea of how do you prove this result. And in order to do that, I will start by telling you how do you prove the classical whole ray. So I want to give you a brief sketch of the proof by Hall that the classical Lagrange spectrum has a whole ray. So I don't know if I should do this. Where should I do this? Okay, maybe I'll start here. So Hall's ray proof for sketch for the classical Lagrange spectrum. Okay, so any question before I move on? Is it okay? Or, yeah, let me check that I didn't forget to tell you anything. Ah, yes, I did forget to tell you something. Yes, so maybe this I'll put here. So first of all, actually we were kind of surprised because when you take a Veech surface, the locus is actually just a hyperbolic, unit-tangent bundle of a hyperbolic surface. And as I said, there was a lot of research on mostly Markov, but also something on Lagrange spectrum for hyperbolic surfaces. So the first thing we thought, oh, this must be in the literature. And actually we looked up in the literature. And so there is a result by Shergon and Schmidt, but it's not about the whole ray, but it's about the Markov, not about Lagrange, but it's about the Markov spectrum. So the Markov spectrum of any hyperbolic surface, of any, let's say they call it Riemann surface. The title is the Markov spectrum of any Riemann surface has a whole ray. So the thing is that the Markov spectrum and the Lagrange spectrum are not the same. And the Markov spectrum is obtained basically considering some soup, while the Lagrange spectrum considering a limb soup. And if you can show that the Lagrange spectrum is contained in the Markov spectrum, but if you prove the existence of a Hall array for the Markov spectrum, it doesn't tell you anything about the Hall array for the Lagrange spectrum. So heuristically, it's easier to achieve a value by constructing a geodesic or geodesic that once goes at a certain height. It's harder to construct a geodesic which accumulates to a certain value. Yeah?
I'm confused. It seems you said the Markov spectrum, on the one hand, you say it's the soup, right? So you take limb soup.
Yes, yes.
On the other hand, it's the piece, the first discrete part of...
The first discrete part is the same because they are closed sets and they are discrete. So soup and limb soup along a closed orbit, there's no difference. So the logic is that when you are discrete, because closed orbits are dense, the values have to be achieved by along a closed geodesic. And if you look at the closed geodesic, if you have the soup or the limb soup, it's the same.
Yeah.
So that's why they are the same.
But does the Markov spectrum not contain the Hall array, or does it contain the Hall array?
Markov spectrum also, the result is for a Hall is for Lagrange spectrum, but it's a good question if the classical one should be known, but yeah.
You just said that the Markov spectrum contains the Lagrange. I thought it's the other way around.
No, I said that no, Lagrange is included in the system, right? Yeah.
But if the Lagrange contains a Hall array, then and is included in the
yes.
Then the Markov contains.
Yes, but for the for the classical one, you're right. For the classical one, once you have Lagrange, you have also Markov array. That's the answer. Yes. For the classical spectrum, but I want to prove it for Veech translation surfaces, right? It's a different question. So you're right. I was thinking, oh, I don't know the reference that the Markov spectrum has a Hall array, but Hall proves that the classical Lagrange spectrum has a Hall array, hence.
It's just a matter of definition. I was under the impression that the Markov spectrum is only the discrete part. It does not it includes the Hall array and everything.
Yeah. Yeah. I mean, it depends. Yeah, it can be fine. Okay, so can I go on the sketch of classical? Are you ready for that? So hopefully this is independent on translation surfaces, so you should. So first step, and I don't have time to prove, but it's actually easy. So first of all, let's say that alpha, you know the continued fraction of alpha. So alpha has entries A0 plus A1. I'm using this notation, A1, A2. I'm using the bracket notation for the entries after the integer part. So by this I mean A0 plus 1 over A1 plus 1 over A2, so on. So let's say these are the continued fraction entries. So first of all, you can rewrite your limb soup. So first of all, you can show that you can just take P and Q to be convergence. It's enough to look at convergence, and these areas would be, limb soup of the area would be achieved by convergence. And then if you look at convergence, you can actually rewrite these quantities very explicitly in terms of continuous fraction entries as follows. So you're going to have a quantity which has mostly depends on an, and then the future has the form an plus 1, an plus 2. So this is the continuous fraction from an on. And before, I hope I have enough space, I want to put the backward continuous fraction. It's a finite continuous fraction from an back to a0, an minus 1. So sorry, this is the limb soup of this quantity. So again, this quantity, it has this integer part, it has this an, and then it has two tails. And these two tails are numbers, for how I define this notation, these are numbers between 0 and 1. So I'm adding two numbers between 0 and 1 of which depends only on the future after n, and one of which depends only on the past after n. Does it make sense? Okay. So this is simple manipulation. It's actually quite easy if you know the recursive formulas for Pn and Qn. You can, if I had time at the end, I could do it, but I won't have time. Okay. Let's believe this formula. So, and I'm going to use continued fractions now. So the second step is the following. Let me look at the following set. Let me call it Kn. So let me look at the set of all numbers, which I can, all continued fractions of numbers that I can construct with bounded entries. So let me look at all continuous fraction that I can construct where my entries are bounded to be capital N. And again, by my definition, this is a subset of 0, 1. And if you look at it, you see this is going to be a counter set. So I want to make some gaps, and then I can have a counter set structure. And you can study, how should I mention, you could study the gaps, the size of the gaps in these counter sets. I should have erased the main theorem, but okay, it doesn't matter. I'll continue here, so I think I'll finish in this board. And so the main theorem that Hall proves is that as long as n is actually greater than 4, if I look at the sum of two of these counter sets, so this is the sum of numbers in 0, 1 in this counter set, this actually contains, I don't know, it actually, okay, contains an interval, and an interval of size 1. Contains an interval of length 1. Okay, so I'm summing two counter sets of size 1, and the sum contains an interval. And this is really the crucial step, because now, how do I end the proof? Okay, now I want to finish this proof. So now, take any L which is greater than 6. That's where the whole ray begins. And so by step 2, I claim that I can write L as k, some integer part, which is going to be greater than 6, plus a number between 0 and 1 that I can write as in the sum of the counter sets. So a number, by definition of counter sets, I can write as B0, B1, dot, 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 plus A0, A1, dot, 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 where AI and BI are bounded by 4. Okay? By the sum of the counter sets. So this is the integer part, and the fractional part, I can write it is in the sum of the counter sets. And now I'm essentially done, because now the trick is I claim that I can construct a value which achieves L. I construct an angle whose continued fraction, I can define the continued fraction of an angle which I want to find a theta such that L of theta is equal to L. And I will do the following. Let me not define it properly, but I want to construct a continued fraction which looks like this. Infinitely many times I will see k, and in front I will say A0, A1 up to AN, and before I will see B0 up to Bn. And so I stuck in the continued fraction expansion blocks like this with larger and larger lengths. And then, okay, then you can convince yourself that if I compute the value when I'm here of the Lagrange spectrum, by the formula that I had, the value will be k plus the two tails. And the two tails are chosen so that the value is exactly L. And this bounds, the fact that it's greater than 6, I need it because I want to make sure that the lim sup is achieved exactly at that moment, at the moments where I see k, and not in some other moments. And if I put myself somewhere else, the entries are bounded by 4. So, and the sum of the value is going to be 4 plus at most 2. So the values will be less than 6 at any other point apart when I see k, which is greater than 6. So this shows you that this sequence where I see k actually realizes the lim sup. So I don't know, it was a little bit fast, but this is really the idea of the whole ray. And now I have 15 minutes, which was even less. And I want to at least give you a flavor of what do we do. So our idea is exactly to use the same classical argument of Hall about sums of counter sets. But what we need is really a formula like that. So we want a formula for any Veech surface, which using a suitable continued fractions gives the values of the spectrum as a sum of two counter sets. And here I'll try to give you a sketch of. So what do we do? Actually, we use, okay, a variation of the continuous. We use a, okay, so let me take S Veech. And I'm going to look at, this is going to be the SL2R orbit that I'm going to draw as a disk. This is like SL2R. I'm thinking of this unit tangent bundle as SL2R. And let me say, let me assume, and I can assume up to a finite cover. that my Veech group, I look at the finite cover of the Veech group that I'm going to call gamma again, which has a fundamental domain, which is an ideal polygon. A polygon whose all vertices are on the disk, which has D fundamental domain, ideal polygon, ideal fundamental domain. Let me write it like this. Okay. So basically, I want to construct a continuous fraction ad hoc using this domain. And this, what we do is essentially, we want to use, this is an idea due to Bowen and series. We want to use Bowen and series symbolic coding for the geodesic flow on this, for the geodesic flow on H mod gamma, okay? So, what is the main idea? I think I need a good, very good picture, which maybe mine is not. First of all, this disk, it doesn't look like a disk at all, but well, it doesn't matter. It's maybe too small, but okay. Okay, I'll just give you the flavor. So the sides of this fundamental domain are identified in pairs. So you can maybe call them, we need another color, alpha, alpha bar, beta, beta bar. And there are generators of the Fuchsian group which map, say, the side alpha to the side alpha bar, and the side beta to the side G bar. So G alpha are generators. Well, G alpha maps a side labeled with E alpha to a side labeled with E alpha bar. So I choose the labels to come in pairs. Okay? And once you gave a label to the generators, to the sides of your ideal polygon, so let me maybe erase these generators now. You can actually, because this is an ideal polygon, so first of all, there is a tessellation. I'm just drawing at random now. You take your ideal polygon, you reflect it through the generators, and you get a tessellation of the whole disk into ideal polygons. And the labels of these basic sides transport uniquely to labels of all sides. This essentially, I'm using the fact that it's an ideal polygon. So there is a unique way to write any other copy as a product of these generators and without cancellations. Okay, let me not spend. So in any case, these labels carry around. So the labels will be, well, I'm doing it at random now, but you can define these labels for the whole tessellation. And then, okay, then I want to define the symbolic coding. Okay, let's look at my surface. So I had a surface. And this you should think of as the space of deformations of my surface. And you can identify the center of the disk with the surface I'm looking at. So now let's say that I'm interested in studying a certain direction, 0 is less than theta, less than pi, on my surface. And if I fix the center as my given surface, as I change direction, I have to look at different unit tangent vectors at this point. So rotating the surface means changing a unit tangent vector in this picture. And if I want to study r theta, I want to look actually at the, I want to look at the geodesic ray which comes from the center and points to some point of the boundary which is parametrized by theta. So you can think of the boundary as being parametrized by angles between 0 and pi. And as I change my angle between 0 and pi, I'm looking at a different geodesic ray from the center. And to one of this angle theta, I want to associate the symbolic coding given by Bowen and series. So I want to associate, as I travel along this ray, I can record the labels of the sides that I hit in the tessellation, okay? Associate a sequence of labels. And these are, maybe I'll erase this picture. Associate as a symbolic coding the labels of sides crossed. And this is essentially almost a full shift. This is the sequence where the unique restriction is that the next label cannot be bar of the previous. There is only a simple non-backtracking condition about what can happen, but okay. So this is basically a Markov shift. And this is used by Bowen and series, use this coding to produce to code a section of the geodesic flow by a shift of finite time, by in this case a Markov shift, through what they call boundary expansion. This is actually the boundary expansion of theta. Okay, so I have one extra step that I need to say, and then. Okay, so we want to connect this boundary expansion in the hyperbolic world with areas of saddle connections. So to each side, I hope to state one more thing. So to each side E alpha of D, I want to associate a wedge. So a wedge, it's a pair of vectors. This is a pair of vectors V alpha right, V alpha left. So this is a pair of vectors in R2. And how? What are these two vectors? So what are these two vectors? V alpha right and V alpha left are the shortest displacement vectors in the direction, so sorry, my side E alpha has two endpoints that correspond to two directions, say in the directions E alpha R, E alpha left of endpoints of E alpha. So let me explain. So I look at the side, and I look at the two directions which represent the endpoint. And you can show on the Veech surface that these are so-called parabolic directions. So there are actually plenty of saddle connections in that direction. There are actually full cylinders. Okay. There are plenty of saddle connections in these two directions. And for each of these two directions, you look at all saddle connections and you pick the shortest. And that is the one that I record here. That doesn't make sense? And I want to state, okay, this is the basic. For each edge, I associate for each edge of my fundamental domain, I associate one wedge. And then, so if theta has an expansion alpha n, we can define a sequence of wedges, define omega n, maybe I'll write it like this, a sequence of wedges, by starting from these fundamental wedges and acting linearly by the generators, which, let me write. I'm going to take G alpha 0, G alpha 1. These are the generators of the group that they act hyperbolically as Möbius transformation, but they also act linearly as matrices in R2. So I stop it at alpha n minus 1, and I apply it to the wedge alpha n. So essentially, I take my basic wedges, I take the generators associated to the symbolic coding and apply linearly. And you can prove that these wedges produce, if I have a direction theta, what I'm constructing a sequence of nested wedges which tend to the direction theta as n grows. So and I claim that this is going to give me a sequence of saddle connections which approach theta. And I claim that these are exactly the saddle connections where you want to look to compute. So now I think I'll finish by stating two propositions that give you the flavor of the proof from here, and then I'll stop. So the first proposition is that you can really use these wedges constructed by the symbolic coding to compute the Lagrange spectrum, at least for high values of L. So maybe I'm trying to cite proposition 1. So if L is greater than some constant, it depends on the surface, then, and you look at the value L theta, which is, no, sorry. Write it like this. If L theta, if the value of L theta is greater than a certain constant, from a certain point on, you can actually compute the value, let's call it LS. This is horrible notation. LS bar, let's do this. Okay, then you can compute this lim sup of the areas by looking at only the special wedges. So I'm going to write in words. Smallest area of saddle connections in Wn. By this I mean I took my theta, I have a wedge, and I can compute, maybe I should write with respect to theta. So I have a direction, I have a wedge. There are two saddle connections in this wedge, and I can compute the area of the rectangles in direction theta and pick the smallest, okay? And I just need to look at these saddle connections to achieve the lim sup. And maybe I want to say a remark, is that Mauro Artigiani actually shows that this is through the proposition, that maybe let me call it, that this fact that you can use this sequence to compute the spectrum star holds for every value in the spectrum for regular polygons. So if you take the regular octagon, for example, not only you see large values in the spectrum, but you actually see the whole spectrum using this continued fraction. And maybe so this is a good continuous fraction to study the spectrum of Veech polygons. And at least for high values, you can use it for any Veech translation surface. And finally, the second proposition basically tells you that these areas of wedges can be expressed using a formula like the classical one. And this is where I actually think I should lie. Maybe let me lie with some assumption. Essentially, I want to say that this smallest area of Wn, if alpha n is given by a certain alpha, if you look at times, then you can write this as, let me lie, I'm going to write something like this. Okay, I have to write it like this then. Say that you have, in your continuous fraction at time n, you see k times the letter alpha. I'm lying too much. Okay, let me not lie. Let me forget about this. Okay, let me just write this. Let me just write that there exists a certain, okay, let me write like this. You can use the you can construct a special continuous fraction expansion. And this is, okay. Maybe I'll write like this. So I claim, so if you look at alpha n for which the entry is alpha, there exists, this is the alpha backward continuous fraction. There exists a continuous, an explicit continuous fraction that I cannot really write now. There exist two continuous fractions, a forward and a backward continuous fraction. And by continuous fraction, I mean ways of achieving a number as product of matrices in projective action. Okay, so that you can express the area as sum of the future continuous fraction plus the backward continuous fraction. And then basically you can play the same game that whole. And then you see kind of the sum of counter sets. And I think I don't want to abuse of your time, so I will stop here. Okay. Hopefully it gave you the flavor of the proof and the flavor of the tools.
Questions? So is this completely hopeless for something like the golden eigenform locus or something?
As what?
Like it's something which doesn't have very good coding theory, like golden eigenform locus, for example.
Yes, yes, yes.
So probably the same theorem is true, but is there any hope to prove it using these methods?
Yeah, I don't know. But first of all, I should say that in the main paper about the Lagrange spectrum with Pascal and the others, we have a formula using Rosevich induction for any. And what is funny is that this formula, you would think that Rosevich induction works well for only for the full stratum of the connecting component. But thanks to your result, Actually, we showed that this formula is good for any locus. So for any variant locus, you have a formula using Veech induction. So, no, you're right. But then you don't know exactly. No, I'm saying something silly because you don't know exactly. So I will, okay, no, you're right. I don't know. I wanted to say, but then you cannot do sum of counter sets if you are in higher dimension. And in this case, you actually don't know exactly what the counter set leaves. So no. No, we were using this formula for doing closure and density because when you do closure and density tricks, you don't leave the locus. But no, to do the whole ray, I don't know, even for the, no, I don't know. So it's not clear, you're right. There should be a whole ray, but it's not clear how to prove it like this, yeah. Yeah, so I don't know. Yeah.
So if you play around and instead of defining it, the Lagrange spectrum for a direction,
yeah,
you define it for a ray in the translation surface.
What do you mean?
So if you start at a 0, and you go in some direction, so
yeah,
there are many, like if you fix a direction, there are many rays that go.
I don't know, I understand. You want to specialize, you can certainly do with this machinery too, because you can define, instead of one single, this wedge doesn't exist, you can define a set of wedges, one per each plane. Sector, exactly, one per each bundle of saddle connection look, I would say, okay. But, and then you can keep track of all of them, and you can have the formula in each, I guess. So no, but then I don't know exactly. No, I'm not sure. No, I'm lying. Yeah, you can in principle use set of wedges, but then you don't. I don't know how each transforms. Okay, we can discuss this later. Okay, we can discuss.
Another question is,
yeah.
How do you get rid of the assumption that you were finite covered?
You don't get rid, because actually my surface, I keep it what it is, just to do coding of the, I take whatever the Veech group is, the fundamental domain, and I use, to do coding, I use the finite to one cover. I code with respect to, but I don't need to do, I mean, I'm coding the geodesic flow for my quotient of the Veech group, but I'm coding with respect to the finite to one cover. It doesn't matter, yeah. Yeah.
Does the start of the Hall rate depend only on genus, or could it go to infinity?
That's another good question. So there is a trivial bound on the beginning of the spectrum, which depends on genus and number of singularities of the stratum where you lie, which essentially is just a rephrasing of an upper bound of the systole. For example, you can find in Weiss's Smiley-Weiss paper. But actually, another thing which is a good question that we thought a little bit about, but we don't know the answer, is what is the Hurwitz constant for even for the full stratum, the full connecting component of, and I don't know, and it's something I've thought a little bit, but it would be nice to know the Hurwitz constants.
Is the Hurwitz constant the shortest geodesic?
It's not the shortest geodesic. It's not clear at all that it's related to that. This famous question that people study is the smallest dilation of pseudonosovs, right? Here we are looking, it's not clear it's the same. You're looking for the smallest compact set, which contains a closed geodesic. So it doesn't have to, it could be that there's one which is longer than the, it might be the same at the end, but a priori you could have another one which stays in a smaller.
You could have one that's very long, but it wraps around very efficiently.
Yeah, so there's one inequality which is obvious, but it's not clear that, and it's of course that the guess would be, yeah. And actually, I think for H2 and for, I think now we know how to plot. Another thing is you can use this diagonal changes. This is another induction that I've talked about before. I think you heard. That is very good for computing this Lagrange spectrum. And when Sun has run a code for doing it, and it's very efficient also numerically because it has much better than train tracks. And so you can actually probably plot the Lagrange spectrum, and you can actually might find the numeric, I mean, proven computer-assisted. But it would be nice to have a geometric argument of what it should be. But yeah. So, yeah.
Can you do anything if the field is changed?
For what?
The underlying field is changed, not the rails.
Field is changed? No, I don't know. Not the real. No, but maybe I should say that Mokuran, for example, for imaginary quadratic fields, and this is related to the Bianchi group. You can do this type of Lagrange spectra or macro spectra for the Bianchi groups, and then you get, for example, results about Diophantine approximation in imaginary quadratic fields. Does it make sense? You can Yeah, so
Okay.
maybe
But
it's not,
that seems
that's
okay.
been done. I mean, I don't know what else you want to, you might have different questions, but
No, I
some
mean,
of it has been looked at, yeah.
I mean, I'm guessing that I would guess if it was a field form of passives, it would, a lot of this machinery would go across without too much difficulty. Maybe not the geometry, but
Yeah, I don't know. No, actually, this Corinna was using the geometry to prove results in number theory. That was his philosophy. And Polan has used this philosophy a lot. So Polan has found lots of number theoretical results using this geometric interpretation of penetration spectra, approximation spectra, and variations. But yeah.
It's the analog of Cusic's theorem known for diagonal flow on SL3R.
But then it's a different story. But then you have this problem that it's always discrete. You don't have what, I think.
Well, we don't know all the.
I think you are at the issue of Oppenheim from judgment. So I think you have discrete stuff. You don't have these pictures like Lagrange Hall ray. You don't have a Hall rays anymore. And
I thought that's no open problem.
I don't know. I don't know. To be honest, I don't know. I'm not the person to ask to. So yeah.
Okay, so
Yeah, I like.